And so now I'd like to introduce our speaker of today. So Viviana is an associate professor at City University of New York, City Tech, and also at the Graduate Center. She's also an associate member of the Center for Computational Astrophysics in New York and a visiting scientist at the American Museum of Natural History, and a Harlow Shapley visiting lecturer for the AAS. She did a bachelor's in Pisa and her PhD in Trieste, both in Italy. Viviana is an expert on the interface between astrophysics and data science, and she will talk about that for us today. She's given many talks on the subject for both astrophysicists and for data scientists, and has received many accolades for her work in tech. And she's currently also writing a book for Princeton Press about machine learning and astronomy. So you can all look forward to that in a bit. But first, she's going to talk to us about her work. So Viviana, all yours.
Thank you, Chiska. It was, it's really a pleasure to reconnect with you and to meet all of you, even in this, format that we have grown accustomed to, but it's still strange. So it's really a pleasure to be here. And, this is my title slide. And so, this is my official title, which is Understanding the Universe Through Distant Galaxies. But you will discover pretty soon that I'm not going to talk much about understanding a universe, and I'm not going to talk much about distant galaxies. In fact, this will be a better title for this talk, as a lot of what I do is really trying to understand how we can squeeze information out of spectra of galaxies that we see. And so, still, it's nice to put this in context. And so in general, I think that if you have to spend a lot of time studying certain objects, I think galaxies are an awesome choice. First of all, they are very bright, so you can see them from very far. And they have been around for more than 95% of the life of the universe. Of course, if you want for something you can see from very far, you should make sure that it was there at that time as well. And so this is also a check. And then more in general, there's a lot that can be done in terms of astrophysics and cosmology, which was, one of my first interests with galaxies, because they're sensitive both to the expansion history of the universe as a whole, and also to the way the structure grow and develop. And so we can learn a lot from them. But as I said, I'm not going to talk about any of that, and I'll focus instead on how we can study them and what kind of information we can hope to get out. So the idea here is that if you study galaxies, you usually have this problem that what you have is some form of emission charge at different wavelengths. But this is not what you would like to have, because you're interested in inferring physical properties of galaxies, things like how much mass there is, how they assemble the stars, what's a distribution of dust, what's their chemical enrichment history, how far away they are. And so, how do you go from one to the other? Well, for a very long time, the name of the game has been spectral energy distribution fitting, which is a process in which, again, you sit in front of your computer and, I'm aware that this data look pretty bad, but this is actually the first galaxy data I worked on. And so I do have an affection for them. It was, well over a decade ago. So you have some, fluxes or measurement of luminosities in some bands. And then you say, okay, I want my physical properties. And you realize soon that you need another thing at least. And the other things that you need are models. Because when you have models, then you can start doing things like these. You try a model. This is the red model. It's not great. So you try another model. Here, this blue model. This one, it's a little bit better in terms of going through the data, but still not awesome. And maybe you continue and, you try this other model. This other model, actually, it's quite good at, we say fitting the data. In practice, it means going through the points. And then at that point, you can use the fact that you know the properties of your model galaxies. And if the model galaxy resembles the data, you can say, okay, in this case, I also, like the properties of the observed galaxy should be similar to those as well. And this is how this works. Now, in practice, you want to have a way of doing this automatically, right? We don't want to try and, keep trying models the way that I showed. And so again, about a decade ago, when I was a naive postdoc, I wrote an algorithm to do that. It was called GALAXIES. And at that time, it was the first publicly available algorithm for SSD fitting that did a Markov chain Monte Carlo exploration of parameter space. There just wasn't much of this at the time. And I wrote another one the year later that was quite a bit faster. And by now, they have both been retired. They're actually, really out of shape compared with the things that we have now. And in just 10 years, we've seen a proliferation of tools that we can use. So, this is a slide that I keep updating every year or two, and I'm sure, I'm missing something, but there's just like a full zoo of spectral energy distribution fitting tools that we have developed. So this part has been really exciting. And I want to talk a bit about, what we have learned and what we have not learned yet during this time. So there's definitely been a lot of great developments and, great successes in the history of SED fitting. I think some of them are technical. So for example, we have learned how to build more flexible models for the stellar populations. We have learned more efficient ways to explore parameter spaces and infer our parameters. And so this has been inducement becoming a lot faster. We tend to program these things and to write our algorithm in ways that are easier to use. For example, now there are a lot of more of these are written in Python compared to compiled language like Fortran or C. And we have, learned more about the distributions that we're looking at and, what kind of algorithms are suited to explore them. And then, of course, perhaps more excitingly, even, we have, learned a lot of things about science. And so, in my opinion, the most significant things that we have learned how to do is to look at spectral energy distributions all together. I feel like, when I started, a lot of the surveys or the data that I had, they pertain to one specific and small region of the electromagnetic spectrum. And this is always something that causes biases or, there's a lot of missing information. When we put the whole picture together, we can learn a lot more. And this is something that for now, we have millions of objects for which we have this so-called panchromatic picture. I kind of hate to use the word panchromatic because I think that astronomers love it so much. It's everywhere, but it is what it is. So, okay, full spectrum. And then, I think we have made a lot of progress in modeling things like emission lines and dust attenuation. We have seen some convergence in, aspects of, how we model stellar evolution. For example, things like, TP, AGB stars, this particularly thermally pulsating, I should say, asymptotic giant branch stars. They were a hot issue 10 years ago and now not so much anymore. Well, we have learned that it's good to put error bars in plots. And, we have learned that when we look at parameters, we should really study them together because, they have degeneracies and they have correlations, and we have explored them quite a bit. We have been able to harness the power of cosmological simulations to inform the models that we use. For example, now I think it's much more common to have the notion of stochastic star formation histories in the sense of, something that, it's caused at a certain point by a traumatic event like a merger. And finally, I'm sure it's not a complete list, but another thing that we have done that I think is meaningful is that we have understood a bit better what parameters we should use to describe galaxies. For example, we used to fit for age as the time from the onset of star formation. And now we realize that we don't have a good handle on these parameters, and we tend to use things like the median stellar age, which is on the one hand more significant for the evolution of a galaxy, and on the other, something that we can measure better. So these are all great things. But then, of course, you can also write the other side of the story. And I think the other side is the fact that, this was already true 10 years ago. In fact, this plot comes from, a 2011 paper. And just the fact that the assumption that we make when we do spectral energy distribution fitting can't, affect our result more than the errors due to the photometry do. So in this case, what we were trying to do was reproducing a result from a paper from 2008. And it was the same exact data. And this was, me trying to work with my code and, test it. And we realized that we had a big difference. And then, walking this back, we saw that we were making some, what we thought were slightly different assumptions in our SED fitting modeling. And yet those reasonably close assumption, gave us a shift of a factor of 3 in things like masses and ages. And you can imagine that the better the data become, the more this issue becomes significant. And we have realized that there are some parameters that are affected more than others. So another thing that now we know very well is that when we make assumptions that are simplistic, and here one of the examples is for star formation histories, which is a topic very dear to me. So let's say, for example, that we have a galaxy that from simulations we know it has a fairly complicated star formation history, which is described by this dashed black line in this plot. And then normally this is not the model that we assume. Normally what we tend to do is that assume that the star formation history exists in some form, in some sort of functional smoothed form. We use a model for that. And so you can see, all these different lines and colors correspond to using a certain model. And each one of them gives a bias in the properties that we derive, for example, masses or even more star formation rate. And, we don't even want to get started about ages. And most notably, all of these methods tend to create a bias towards younger stellar populations. Something that sometimes we refer to as outshining. So stellar populations are actually older, but we tend to be attracted by shinier objects, and these shinier objects are usually young. I actually looked at this a little bit more in detail, even a few years back, again with simulations. And what we did was, take mock data and trying to inject different sources of error. That, these are known sources of error. These, for sure will be there. And we sort of, looked at the ones that induce the worst biases. And again, we found that simplistic star formation histories were the worst offenders, in the sense that when we parameterize star formation histories poorly, we hurt all our inference in other physical properties. So these are the ones that have the highest reach. So all in all, we still have a bunch of open issues. I feel like that, uncertainties that we put on our measurement on the basis of experimental errors are certainly underestimated because we don't include modeling uncertainties. We have these issues of the biases versus younger stellar populations. And this is, strongly driven by poorly parameterized star formation histories. And, a bunch of other issues, such as the fact that we still have different and not in agreement libraries of stellar models. And the fact that all this assumes that the initial mass function is constant and known, which is obviously a gross approximation. But I feel like, notwithstanding all of these, I have to say that I love SED fitting. It's not perfect, but I think it's great. I work on this for a long time. It's what it got me my faculty job. So I will forever be grateful. But sometimes the heart may be a wanderer. And so a few years back, I started thinking about, are there maybe other possibilities, other ways in which we can start thinking about inferring galaxy properties? And they started working on a project on using machine learning to measure star formation histories of galaxies instead. So, and this is work with Christopher Lowell, who at that time was a graduate student who visited me for 6 months, and now he's a postdoc at University of Hertfordshire. So what was the idea? What we thought is that maybe one thing that we could try doing is the following. We know that we have cosmological simulations that start to be good enough to believe them. And so we're thinking of things like lost trees and eagle. So those simulations have the advantage that they give us realistic star formation histories. So we could take the star formation histories from that and then use some stellar population synthesis modeling to create spectra. And then we are attempting to teach neural networks, actually, different models, but in the end, the most successful one was a neural network, to learn the relationship between the observable, which are the spectra, and the star formation histories, which is what we want to learn. And we thought, okay, we'll do that. And then we can see how our model, whether our model is robust to using, not one, but different simulations. So we train our models. And this is an example of our results. So on the x-axis, you have look-back time. We decided to divide look-back time in, I think, 8 bins. They are uniformly spaced in log of look-back time to reflect the fact that we are more sensitive to recent star formation histories compared to very remote times. And in each one of them, we're basically assuming that there is a constant star formation rate. This was like the best thing we thought we could do to not use a model for these. And so on the top left, you can see a case for which our star formation reconstructed model works really well. And not surprisingly, is a red and dead galaxy where all the star formation happened at a very remote time. And then as you sort of move through the plots, you see examples where we don't quite do quite as well. And the one on the bottom right is one in which we are severely underestimating the amount of star formation that we see. And maybe this is because of the generalities. These are they can be dusty galaxies and so on. But the idea in general is that we thought that overall this worked quite nicely. The metric that we use to measure these, I should mention, it is something called SMAPE, symmetric mean absolute percentage error. I could go over why we chose that, but we can think of this as something that behaves more or less like a percentage error, at least in the low error regime. And so you can see that, when, of course, the results that we report are on so-called test objects. So these are galaxies that have not participating in the building of the model, which, sounds like great news. I mean, this is the right thing to do, but it's still extremely optimistic, for all practical purposes, in the sense that basically you're assuming that, you're applying your model to objects that are statistically indistinguishable from the ones that you use to build the model, right? So, they were not there, but they are drawn from the same distribution. So it's very comforting that the method works, so that you can get star formation histories, with this kind of accuracy, like 10, 20% in each of the bins. But of course, what you really want to ask is like, okay, what happens if, now you apply this to objects that are from a different simulation, which is not quite as good as asking, what happens when you apply this to data, but, it's a step. And so for this, we did the sort of cross exercise of building the model using one simulations and then testing on the other. And here on screen, you can see that, the sort of median SMAPEs, they shift. It's hard really to explain, I don't really actually want to quantify this, but I think, something that we can say is that when you train on one simulations and you apply to the other, this mate doesn't blow up. And so, it increases, but, it doesn't go completely crazy. And we thought that this was a good enough result to deserve a victory dance. So at this point, as I mentioned, we were, like quite happy. But for me, I had this nagging feeling that, no matter how you phrase it, no matter how, different your simulations may be, I feel like at some point you need to face this harsh truth that, you're training the model on simulations. And in simulations, you know what the ground truth is. Right? You know what the real star formations are. And you can always figure out what kind of error you're making. And, on real galaxies, and this is, a very general problem, I think, in astro, nobody is there to tell you what those labels are. Nobody is there to tell you, how these galaxies really assemble their star. And so just the idea, having a matrix that depends on this was, at least for me, very unsettling. And so I started to think a lot about, what would it take to trust these machine learning models that we build when we apply them to data. And I think, in general, hopefully you would agree with me that if the simulations were just perfect, if the simulation looked exactly like the data in every minute detail, then I think, we could probably all agree that they are trustworthy, right? If they resemble what we observe in the universe. However, probably even if the simulations were very similar to the data with some small differences, I think we can agree that, the models that we build on simulation should still or would still retain at least some degree of reliability, at least some degree of trust. And so I've been, spending a lot of time thinking about how we can leverage this notion of similarity in the space of observable, right, in the space of spectra, and see if we can conclude something on, how trustworthy our models are, or maybe, like to be a bit more precise, what is the error that we make when we measure physical properties. So I'm going to try to explain this a little bit more. This slide, I think, has a lot of content. So let's see, we have, like the domain of the application, which is the domain of data. And then, we have the domain that we use to build our model, like the training domain in machine learning parlance, which are the simulations, right? And, we have the space of observations, which are the spectra. And so I want to say that these, weird shapes that looks, I feel like the left one looks vaguely like a heart. It's nothing mysterious. They are populated by spectra. So these are, the spectra that we observe and the spectra that we simulate, okay? And in this space, this is a space in which I can formulate some notion of distance. I can, somehow come up with some measure of similarity. Then I have my space of inference, which is the space of the physical properties. And so for the data, these are like the true physical properties of galaxies. And, there is some function that is unknown to us, but, it's known to nature, that says, okay, if there are some physical properties and, many latent variables here, then this is how the spectra will look like. And this function is what I'm calling f. Now, of course, also in the space of simulations, I start from some physical properties, and I have a function, which is my modeling function. This is known, but not perfect, that takes me to the space of simulations. Now, what I would really like to know is what is the inverse of this function f, right? On data, how can I, start from data and, go to the true physical properties of galaxies? And this is, of course, something that I want to do, but I don't know how to do. But instead, what I can have is, as a proxy, as a surrogate, is the inverse of the function g. This is something that I can learn. when I set up my machine learning models, what I'm learning is this inverse function, right? That takes me from the simulated spectra to the physical properties of galaxies and simulations. So what I'm saying here is the following. Let's say again, just in the space of simulations, I start from some like input physical properties. I go through my function G, which is known, to my space of simulations, and then I learn the inverse, and so I derive some physical properties. I showed you an example for the star formation histories, and of course, even in the pure space of simulations, these properties are not exactly the true one. I have an error, right? I make an error, and my error in general will depend on the experimental noise that we have, and then it's typically decomposed in a bias and variance for machine learning models. But whatever it is, I know that my measurements, my inference are not perfect. Now, what I'm saying is, what happens if I now move to the space of observation, and the space of observations will differ from the simulations, and maybe I can measure this distance with some distance metric that I still have to come up with, but I'll talk about it. And now what I'm saying, actually what I'm hypothesizing is the following. Let's say now that I apply my inverse function that takes me from spectra to properties to the observation. This is the best I can do, because nobody gives me the inverse of the of the true f function. So all I can do is use the functions that I learn. And I will infer some physical properties, which of course will not be the true ones. And just like in the space of simulations, actually, I will have an error. So what I'm I guess hoping to show, hoping to verify, is the fact that the error that I make in this case will be, somewhat similar to what I was doing, that is like method dependence that was happening on the simulation, and you will have an additional term. This term that I call B2 square here, it's, and it's called the B just because I think it will be a bias. And what I'm thinking is that what I would like to show is that this additional source of error is proportional to the distance between simulations and observations measured in the space that I can observe. So this is, what I would like to be true. Now, how can we go about verifying if this is the case? Well, first of all, I need a measure of distance. And so last year I was on sabbatical, so I had a bit more time than the usual to think about this problem. And I want to say this especially for the more junior people here. I spent about 6 months going through a lot of computer science literature and thinking about a million ways of measuring distances between high-dimensional data sets. There's a lot to read on this subject. And guess what? I feel like every corner, every alley I was taking just, was something where, I would find a wall at the end. In the end, I had to, scrap the whole thing. I convinced myself that none of these work and none of these would work. And so I'm going to tell you instead what I think is true now. And I understand that, even as I said, I sort of, I want to laugh at myself a little bit, but I'm going to pretend that that's not the case, and that, and that what I'm convinced of now is the truth, and this is how we move forward. And so the first things that I think I learned is that, when you measure distances between data sets, you are, you're measuring a distance without thinking about what problem you're trying to solve. And this is, like if you read papers on domain adaptations and so on, this is in general the case. For our case, however, I thought, okay, this is not possible. If, say, I'm trying to determine stellar mass, I know that, like the part of the spectrum that is most sensitive to stellar mass is the near infrared. And so I can't use a measure of distance that doesn't know about this. Because, if this is the problem I'm trying to solve, then I want my measure of distance to be more sensitive to distance in the near infrared than in other regions of the spectrum. And if I were to build a model that tells me about dust, then I want to look at the UV and the far infrared. And so what I now think is true is that I need to use a measure of distance that knows about which features, which components of the spectrum are relevant for my problem. And so what I'm using now is just like the mean Euclidean distance calculated on the features that are most relevant to each parameter estimation problem. And so we started testing this idea with stellar mass because it's the simplest problem, right? Because like at zero order, stellar mass is proportional to luminosity. And so, it's a case in which we sort of, know what to expect. And so we thought, okay, maybe it's a good, like testing ground for our idea. So this is the distance that, now we thought, okay, I think this distance could work. Now, what do we do to test whether or not it's true that the so-called generalization error, which is this additional error that I make because I learned the wrong relationship, is proportional to this distance? So again, using data is out of the question. And that's because, I need, for validation purposes, I need to know the ground truth. So what we did instead is that we had 20 sets of simulations. And, we tried to sort of, like explore the different knobs that can be moved around in modeling. For example, how you model dust, which stellar population libraries you use, and so on. Things that are compatible still with observations, but, that sort of like create variance. So we have 20 of them. And for these 20 sets, you can calculate the distances between, each set and the other 19. Okay, so this is your distance. And then we trained 20 machine learning models, one for each set of simulations. So remember those functions g to the -1 that make you go from spectral to properties? Because you have 20 sets of simulations, you can learn 20 of them. So we did. And then basically, we calculated the generalization error, the error that you make in physical properties that you obtain when you use your 20 functions on each one of your simulations set. So this basically means that you populate 20 plots like these. On the x-axis, you have distance metric. Let's say that this is for simulation 1. I will have the distance calculating the way that I told you between simulation 1 and all of the others. And on the y-axis, I put the mean square error in stellar mass that I obtain when I apply each of my 20 functions on my simulation 1 set. And then I ask myself, do I get something that is like, a scatter plot without any correlation to speak of? Or do I see something that is reasonably tight? And of course, I'm hoping for something that is reasonably tight. So I'm going to show you one plot, but I have 20 of them. But I have to promise that this was just chosen because it's simulation 1, not because it's particularly good. Some are worse, some are better. But in general, you find, at least we find something reasonable, right? We found that, there seems to be some regression relationship between this distance and this mean square error. And this is the paper that we just presented in NeurIPS, and mostly I'm quoting this because I'm very proud of my title. But why is this relevant? Well, because in the end, if you can show that this relationship holds, then when it comes the moment to apply this to data, you have the x coordinate, the distance between data and simulations, because this is something measurable, right, that you can measure. And then you have the relationship, so you can read out your predicted error on the y-axis. And so you can obtain an estimate of the errors you make without having to deal or without having to use ground truth labels. And so I think that this is where we are at. We have like a million things to still do, but this was like the first time in a year-long project where, I felt really hopeful about, having understood something. All right, so I mentioned, like a while ago that I was sort of like, temporarily swayed by machine learning, but I do think that, SED fitting is one of my first love, and I certainly hope that we will grow old together. And so another things that I've been thinking of, in the context of SED fitting is how can we use Bayesian model selection to come up with results that, maybe they're not quite model independent, but they are less model dependent. And, the idea of model comparison, sometimes called model selection, is the fact that when you have data, right? And in this, in these plots, like data are blue points. You could, try and fit them with models of different complexity. And if you use a model that is simplistic, it wouldn't be a good fit to the data. And if you use a model that is too complex, it would be a fantastic fit to your data, but it will generalize very poorly. And so, model comparison is the idea of checking whether from the data you can infer what the optimal complexity is. And in Bayesian statistics, this measure of complexity is provided by something called the evidence, which is the denominator in Bayes' theorem that we don't think about it too much when we do parameter estimations, but for these things, it matters. And so for us, this is a work that we actually just put on the archive with Andy Lawler, who is a PhD, well, actually now a PhD graduate in statistics, who was working with me. So we try to use this formula to ask, can I determine from the data galaxy went through, right? So rather than assuming some sort of functional form, can I just think of star formation as a superpositions of significant episodes of star formation? So my base model would be like, okay, there was only one, and then, my more complex model will have two, and I will say, okay, do I have enough justification in terms of how well how much better I can fit the data that, is telling me that a second episode is warranted. And, to do this, we used the ratio of evidence of the two models, and this is called Bayes factor. So I'm going to, skim through this just, in the interest of time, but, happy to answer any questions. So as usual, we implemented this on simulations first, and we used candles like galaxies modeled from the properties found in the 3D HST catalog. So our baseline model, our simple model, is like a like it's a tau model, which is sort of like a model in which star formation proceeds fairly quickly and at some point tapers off. And then we added for these galaxies like a burst of recent star formation. And we wanted to see, okay, would our Bayes factor be able to pick the fact that the true model is this more complex one? And if yes, if not, like in what conditions, in what regimes? And this is sort of like, one simple scenario of the results that we got. So the real model is always the more complex one. So, like the ideal picture for this is that in all cases, the Bayes factor would prefer this 100% of the time. I should put a legend on this plot. So here you can see, going from left to right, cases in which the Bayes factor mildly prefers a simple model. So on the left, these are things that are not good, like, failures, if you will. And then on the right, you have, when the Bayes factor is, strongly suggesting that the more complex model is correct, which is good. And so, we saw this as, function of signal to noise. And so we thought that this was quite encouraging. You see, at the current level of signal to noise in the data, which is, 3D HST, not only you have a few failures, but, like in most cases, the Bayes factor wouldn't lead you astray, but wouldn't tell you much either. But as you increase the signal to noise, and this is something that, you know, upcoming service will certainly be able to do, then you can see that you still have a number of cases in which, you know, you are not picking the right model, but, you know, you're definitely moving towards a more sensible tool. And so this was actually quite nice and encouraging for us. And, you know, we also explored a few more aspects of these, but I guess the most important one is that we also found, sort of tested, an alternative way to calculate this Bayes factor from simple MCMC, which is normally not something that is possible, but is something that, you know, we could empirically validate. So I think I'll just, you know, conclude here with some thoughts. I would say, you know, SED fitting has been amazing, and you know, it has taught us a lot of things. Also has biases, so it's good to be aware of them. And I think star formation histories are in particular tricky. And I think we are working in a regime where, you know, our modeling biases affect us more than the quality or availability of data. And so we have to fight against those. I think that one useful thing to do would be to use machine learning methods. Of course, you know, we should always be very skeptical of them. But, you know, like more in general, I think the simulations-based inference will have a really huge role in astrophysics in the upcoming decade. And so, you know, thinking of ways of how to validate things that we learn on simulation is very important. And then I wanted to, you know, conclude with maybe a more uplifting thought, which is the fact that, you know, we can all agree that 2020 kind of sucked. But I think, you know, we've also seen, you know, science at its best, you know, with things like, okay, you know, we developed a COVID vaccine, which is very effective in less than 1 year. And so, you know, I'm trying to think of these as sort of like a sort of inspiration for doing new things in this upcoming year. And so I wanted to share with you. And so I'll stop here. Thank you.